Hello, welcome to the part 3 of lecture 10 in ML series. In this lecture, we will be discussing how to implement a gradient descent algorithm for solving simple linear regression problem. So let us quickly recall what is a simple linear regression problem. So you are given a data set which has one dependent and one independent variable. Like this example, you have a study hour and an exam score, and you know that there is a linear relationship between y and x, which is of the form y is equal to theta naught plus theta 1x, and the goal is to find theta naught and theta 1 which minimizes the mean squared error, where we are using mean squared error as a performance measure for this task. Mean squared error is the average of the square difference between predicted and actual values. So how the gradient descent works is, initially starts with a random theta naught theta 1 values, and it updates theta naught theta 1 by considering the gradients of theta naught theta 1 with respect to this mean squared error. So it actually updates in the opposite direction of the gradients. So when we consider those, so you will get this equation that a practical implementation by using Python, and for this practical implementation we are using NumPy library. So NumPy library provides efficient representation of matrices and arrays, and it also supports the direct addition, multiplication and transpose operations, which are very useful in the implementations. So here we are defining a gradient descent function which takes that x, that independent variable x, and dependent variable y, that means the training data set of x and training data set of y, and a learning rate parameter, that is alpha, and the number of iterations. So if you recall that the convergence, either you can stop after some number of iterations, or if the error is within some threshold. So here we are using the number of iterations as a parameter which controls the convergence. Okay. So initially we are taking theta as zeros. So here this np dot zeros, it creates an array of size 2 and initializes to zeros. So that means theta naught and theta 1 both are 0. So theta naught is representing the first element of this array, and theta 1 is representing the second element of this array. And we are calculating with those initial values what is the mean squared error we are calculating here. And as you can see, we can directly use this vector multiplication, theta 1 into x, and also we can use an np dot sum which calculates the squares and the sum. And so for every iteration we calculate the predicted value, that is nothing but theta naught plus theta 1x, and an error is predicted minus the actual value, and the gradient of theta naught is 1 by m into that sum of errors, and the gradient of theta 1 is 1 by m into that sum of error into the respective x value. So here we can directly use a star to do this element wise vector multiplication, and we take the sum by using np dot sum. So the np is the NumPy library here. Okay, and once you know the gradients, you know that you will be updating in the opposite direction of the gradients. That's why we have theta naught as theta naught minus, and how much amount that it has to be incremented or decremented is decided by the learning rate, that is the learning rate that we are considering here, alpha into gradient theta naught. Similarly for theta 1, and once after updating the theta naught theta 1, again we are calculating the mean squared error, and every time we are printing both theta naught theta 1 and the mean squared error, because this is helpful to know that in every iteration whether the mean squared error is decreased or not. If it is decreased, then only it is going to the convergence, because depending on alpha value and depending on the parameter values, depending on the actual x and y values, there is a possibility of divergence also. It may overshoot. Okay, so to observe that, we are printing here once after the total number of iterations, the actual theta naught and theta 1 value is returned by this function. So this function takes your training data and a learning rate parameter and the number of iterations, and it returns the theta naught theta 1 values. Okay, so to execute, if you recall that we had discussed, so you just need to click on here this run cell. So if there are no errors, then it gives a green mark saying that okay. So now first we will try to experiment this on our example, that is number of study hours and the scores. So this is the number of study hours 2468, and the scores are 60, 75, 85, 95. So let us consider our alpha as, so let us consider that as 0.01, and the number of iterations, let us suppose we are considering 1000. So, and then, so here gradient descent is called, that function is called with x and y, and a learning rate as 0.01 and the number of iterations 1000. So after running 1000 times, it is going to return the theta naught and theta 1 values. Okay, and as you see that in every iteration this j is decreased. So that means it is going towards the convergence. So if you want, then you can also increase the number of iterations. Okay, so this is, see, after this many iterations you got theta naught as 50 and theta 1 as 5.7, and the error is 0.9. Okay, so now we will try to solve another problem, another simple regression problem, that is finding a relationship between CGPA and percentage. Okay, so you are having a data set which is some 380 students data, where the CGPA and the percentage information is given. Okay, so now we are expected to find a relationship between CGPA and percentage. Let's suppose the relationship is a linear relationship. Okay, so that means percentage is equal to theta naught plus theta 1 into CGPA. So you are expected to find the theta naught theta 1 by using the gradient descent. Okay, for solving this, first we have to load this data set. For that, first to load a data set into this Google Colab, first we have to upload that into a Google Drive. Okay, so first we have uploaded that into a Google Drive by saving it as a CSV file. So this is, once it is in our drive, we can access it. So for that, first we have to give an access of our drive to the Google Colab. For this, we will be using this code, the drive.mount content drive. So if you click on this, it will ask for a permission. Okay, so if it is already mounted, then it's okay, otherwise it will ask for a permission. After that, we are reading this. Okay, for reading these Excel files or CSV files, we are going to use another library called a pandas. So, and it has a library function called a read CSV. By using that, you will be reading this CSV file, and then it will be stored in the column formats. First column is representing X and the second column representing Y. As you know that the first column is having a heading CGPA and the second column is having a heading percentage. Okay, so you can sample CGPA and percentage. So here we are using data.head to print the first 5 rows. Okay, for this CGPA, this is the percentage. Okay, and then so before applying gradient descent, we are simply plotting that CGPA and percentage, the scatter plot, just to see the relationship. As you can see that there is a linear relationship between CGPA and percentage. Once you are confirmed that there is a linear relationship and it is having only 2 variables, simple linear relationship, we will be using a gradient descent to solve. Okay, so we are loading into this X and Y, and then so one of the goals is how to check how well it is generalizes. For that, we are dividing this into training and test set. 80% for the training. On 80% of the data, we will be finding the theta naught, theta 1 values, and we will be testing on this 20% of the data test data. Okay, and then we are here. So initially we are considering alpha as 0.1 and the number of iterations. Then what happens is, as you can see that this is every time it is incrementing and then it is going in the divergence direction. So for that we have to, so to overcome that we have to update the alpha 1. So suppose we consider this. If we consider this, then now you see that in every iteration J is decreased. Okay, so let us do it for 10,000 times. Do it for 10,000 times. Then we are going to get this theta naught and theta 1. So that means now we can use to predict the values, and we test it on the test data. So now test data is having 80 data points. So we are considering one random data. The CGPA is 8.29 and the actual percentage is 78 and the predicted percentage is 77.8. You can run it one more time. So randomly we picked one more data point 8, and for that the 74, and the predicted percentage is 74.9. You can run it one more time. So 8.43 and the actual percentage is 79 and the predicted percentage is 78. So this is how one can implement the gradient descent method. Thank you.